In lesson 1, we will talk about the complex number system. So we will have 4 objectives in this lesson. Our first objective would be to define a complex number. Our second objective would be to plot a complex number in the complex plane. Our third objective would be to work with what's called the conjugate of a complex number. And our fourth and final objective would be to perform operations, arithmetic operations, such as multiplication, division, addition, subtraction on complex numbers. To define what a complex number is, we really need to work with quadratic equations, because the first time we see complex numbers or imaginary numbers are with quadratic equations. The quadratic equation x squared plus 1 equals 0. If I'm trying to solve this equation, what am I going to get? I'm going to get x squared equal to minus 4. Then I'm really looking at x as the square root of this minus 4 with a plus or minus in front. Now, until today, we said, I'm sorry, you got to stop here. You say that there is no real root to this equation because you can't take the square root of negative 4. Well, it turns out you can. You just need to define a different kind of number as your solution. So to define what square root of minus 4 is going to be, we need to first define the square root of negative 1 as I. Now, I, or the square root of minus 1, is the imaginary unit. Okay? It's called the imaginary unit. And once I have the imaginary unit defined as I equal to the square root of negative 1, then I can say, well, I think I can just factor this minus 4 as minus 1 times 4. I'm going to call the square root of minus 1 I. So I'm going to have an I out front, and I have the square root of 4, and I know that's 2. So my solutions are 2i and minus 2i. Well, numbers of the form b times I, where b is a real number, are called imaginary numbers because they are the imaginary unit multiplied by a coefficient. So numbers of the form bi are called imaginary numbers. Now let's take a look at this equation. X squared plus 2x plus 5 equals 0. This is another quadratic equation. Our first instinct is to try to factor this, but we find out we can't. And remember from a previous work that you would use the quadratic formula. And the quadratic formula said minus b plus or minus the square root of b squared minus 4ac all over 2a. Now, the coefficients here are a equals 1 or 2 for b and 5 for c. So when you plug these in, you get negative 2 plus or minus the square root of 2 squared minus 4 times a, which is 1, and c, which is 5, all over 2 times a, which is 1. Now, when we simplify this, especially the discriminant inside the square root, we get the square root of minus 16 here, all over 2. And then we can say the square root of negative 16 is no other than 4i, so we can say negative 2 plus or minus 4i all over 2. And then we can distribute the 2 and we get negative 1 plus or minus 2i. So we have two solutions, negative 1 plus 2i and negative 1 minus 2i. These two numbers are complex numbers. They are of the form a plus bi. Okay? They are of the form a plus bi, where a and b are real numbers. Okay? From this, we can see that if b is 0, you just have the number a, which is still a complex number. So real numbers are special complex numbers. They are a subset of complex numbers. And imaginary numbers themselves are complex numbers as well. They are just the case when a is 0. Okay, so all the numbers that we've seen so far were actually belonging to this superset of complex numbers. Okay, one thing we can do with complex numbers is to identify their real and imaginary parts. Now, when we got a complex number, we label it with a z. Let's say we have a complex number in the form a plus bi. The real part of z is the part that doesn't have the imaginary unit. So it's the coefficient a. For instance, if we're looking at this complex number 2 plus I, the real part, let me call that z, the real part is 2, and the imaginary part is the coefficient before the imaginary unit, or I. So the imaginary part of my number z is simply b, and in this case the imaginary part for 2 plus I would simply be the coefficient before I, which is 1. Now when we plot this complex number in the complex plane, we plot the real part along the horizontal axis and the imaginary part along the vertical axis. So altogether we will be plotting the point 2, 1. Okay? So that will be the plot of my point of my complex number z in the complex plane. Okay, let's say we want to plot another point or another complex number, minus 3 plus 4i in the coordinate plane. What that means is I'm going to plot the point negative 3 and 4. Okay? So the point negative 3, 4 refers to my complex number, negative 3 plus 4i. Now, based on this number, I can also define its conjugate. And the conjugate is going to be especially useful when we do division with complex numbers. We're going to use the conjugate of a complex number directly in the process of division. Okay? The conjugate is defined as with a bar over z, and what it does is simply negates the imaginary part of the complex number. So for this particular z, negative 3 plus 4i, the conjugate will be minus 3 minus 4i. And if I want to graph that in the complex plane, I'm simply going to mark the point -3, -4, and let's say that's the point here. So this marks the conjugate of z, or -3 minus 4i. Now let's do a more complicated type of problem. Let's find the square roots of -5 minus 12i. Okay, I'm going to use all these things that we've talked about so far with this question about a complex number, its real part and imaginary part. Let me say that z equals a plus bi. And by asking for the square roots, I'm simply looking for whatever z squared is equal to minus b minus 12i. So what I'm going to do is I'm going to take the square of this z. So I'm going to take a plus bi quantity squared, and I'm going to set it equal to minus 5 minus 12i, and I'm going to look for a and b. So when I square a plus bi, I get a squared plus 2abi plus b squared I squared. And I want to set this equal to minus 5 minus 12i. Okay? Now, because I is defined as the square root of minus 1, I squared actually equals negative 1. So instead of I squared, I can substitute negative 1. So I'll just have minus b squared here. Okay? Now the real part of the complex expression on the left-hand side is simply a squared minus b squared, and the imaginary part is simply 2ab. So what I can now say is a squared minus b squared equals negative 5, and 2ab equals negative 12. So from this, I get AB equal to negative 6. So now I've got two equations and two unknowns, and I'm looking for A and B. Now we're looking for A and B that satisfy these two equations. So let me try to isolate B here on the right-hand side, and I'll get minus 6 over A. And I can just plug this in here. So I get a squared minus 6 over a quantity squared equal to minus 5. This will give me a squared minus 36 over a squared equal to minus 5. If I multiply through by a squared and I transfer everything to one side, I'll get a to the fourth minus 36 plus a squared equal to 0. Let me rearrange that. So I'll have a to the fourth plus 5a squared minus 36 equal to 0. This will be factored as a squared plus 9 and a squared minus 4. So I can have a squared plus 9 equal to 0, or a squared minus 4 equal to 0. Here I get a squared equal to minus 9, and a and b were supposed to be real numbers, so nothing comes out from this end. Then I'll have a squared equal to 4 here, with a equal to plus or minus 2. And when I plug in a equals 2 here, I'll get b as minus 3. When I plug in a equals negative 2 here, I'll get b equal to 3. So I will have two square roots. My square roots will be 2 minus 3i with the coefficients 2 and negative 3, and also negative 2 plus 3i. So those are my two square roots. add complex numbers, we mainly add their respective parts. So let's say we want to add 2 minus 3 with 7 minus 5i. We will add the 2 and the 7, which are the real parts, and the minus 3i and the minus 5i, which are the imaginary parts. So our answer will be 9 minus 8i. Now to subtract these two complex numbers, we can think of this in two ways. We can subtract the real parts to get minus 5, or we can subtract the imaginary parts to get 2i. Another way of thinking about this would be to distribute the minus sign and then add, which would give us the same thing. Now on to multiplication. Let's say we have the following multiplication problem. 2 plus 3i times 5 minus 4i. What we do is we just distribute. So we say 2 times 5 is 10. Then 2 times minus 4i is minus 8i. 3i times 5 is plus 15i. And then 3i times negative 4i is minus 12i squared. And then instead of I squared, as we did in the last video, we plug in negative 1. So we have 10 minus 8i plus 15i plus 12. And then we combine the real parts as 12 plus 10, or 22. And we combine the imaginary parts and we get 22 plus 7i. Now let's do another multiplication problem. 1 minus 7i times 1 plus 7i. Okay? We can multiply this out as 1 times 1, 1 times 7i, and then minus 7i times 1 is minus 7i, and minus 7i times plus 7i is minus 49i squared. Now notice here that 1 minus 7i and 1 plus 7i are conjugates of each other. So when that happens, the I terms cancel and we simply have 1 minus 49i squared. We may also think of this as a squared minus b squared, where a is 1 and b is simply 7i. So we can think of this first factor as a minus b and the second factor as a plus b. And when we multiply a minus b with a plus b, we get a squared minus b squared, which makes the I terms cancel. Okay? And then finally, our last step is to plug in negative 1 for this I squared. So we get 1 plus 49, or 50. Now this idea of multiplying with the conjugate to make the I terms cancel is something we are going to do in division. Let's now look at powers of I. As you know, I to the first power is simply I. Then I squared, we've already seen by definition, is negative 1. Now what about I cubed? So if we take I cubed, we can think of this as I squared times I. And since I squared is negative 1, we can simply say I cubed is negative I. And for I to the fourth, we can think of it as I squared times I squared, which gives me negative 1 times negative 1, or 1. So the powers over I to the first is I I squared is minus 1, I cubed is minus I, and I to the fourth is 1. And because we get 1 on the fourth power, we go back to the beginning. So I to the fifth is again I to the sixth is now negative 1, I to the seventh is negative I, and I to the eighth is 1 again. So we go in cycles of 4. So for instance, if you're asked to find I to the 190th power, what do? We want to find the number of cycles of 4 that we go through. So we take 119 divided by 4, and we get 47 cycles with a remainder of 2. So after we go through 47 cycles of 4, we're back to where I squared is, the second step in my cycle. So I to the 190th power is simply negative 1. Now let's divide two complex numbers. Say we're going to divide 1 minus 2 with 4 plus I. The key notion in division with complex numbers is to get rid of the I in the denominator. That's our aim. Okay? So to get rid of the I in the denominator, we multiply both the numerator and the denominator by the conjugate of the denominator. It's like expanding the fraction by the conjugate of the denominator, okay? So when we do that, the denominator becomes 4 squared minus I squared, because we can think of 4 plus I as A plus B, and 4 minus I as A minus B. So when we combine them, we get A squared minus B squared, and that's 4 squared minus I squared. And then instead of I squared, we can simply say negative 1. So we have 16 minus 1, which gives us a denominator of 17. Now for the numerator, we're just going to do our straightforward multiplication. So we'll go 4 times 1 is 4. 4 times minus I is negative I. Negative 2I times 4 is minus 8I. Negative 2I times negative I is plus 2I squared. Okay, instead of the I squared here, we're going to plug in negative 1. So we'll have 4 minus I minus 8I plus 2 times minus 1. So we can combine the real parts, 4 and minus 2, and we'll get 2. And we can combine the imaginary parts and get negative 9I. And then the way we write the result is we always write the real part first, which in this case is 2 over 17 minus 9 over 17I. So that's our final answer. Let's do another example. 2 plus 3I over 2 minus 3I. We can just multiply by the conjugate of the denominator again, which is 2 plus 3I. When we do that, the denominator is 2 squared minus 3I quantity squared, and that's going to turn out to be 4 minus 9I squared. Plugging in negative 1 for I squared, we get 13 in the denominator. Now the numerator is simply the square of 2 plus 3I. So when we multiply that out, we get 4 plus 6I plus another 6I plus a 9I squared. Then we plug in negative 1 for I squared, and we get 4 plus 12I minus 9. And when we combine the real parts now we get negative 5 plus 12I. And if we distribute the 13, we'll get negative 5/13 plus 12/13 I. Let's finish our discussion with a situation where we actually solve an equation involving a complex number. Here, z represents a complex number, and I'm trying to solve for z. So I'm trying to find what z is. Well, the first thing I'm going to do is I'm going to isolate z. So I'm going to put all the terms involving z on one side, which means I need to subtract z from both sides. So I'll have I times z minus this z. And I'll have to subtract 2 from both sides. So I'll have that equal to minus 2 plus 3i on the right-hand side. Now the next step is to factor out the z as a common factor. So we'll just have I minus 1 in the parentheses. So I'll have z times the quantity I minus 1 equal to negative 2 plus 3i. And then to isolate the z, I'm going to divide both sides of my equation by I minus 1. Okay, so I'll just have my z equal to minus 2 plus 3i. Let me rearrange this to say negative 1 plus I. And of course, I need to get rid of the I, so I need to perform this division, which I do by multiplying both the numerator and the denominator by the conjugate of the denominator. Okay, and when I do that, my denominator simply becomes 1 minus I squared, which gives me 2 when I plug in negative 1 for I squared. I'm going to quickly multiply out the numerator, so I get negative 2 times negative 1, which is 2. Negative 2 times negative I, which is plus 2i. 3i times negative 1, which is minus 3i. And then 3i times negative I, which is negative 3i squared. When I plug in negative 1 for I squared, I think I'm going to have 5 minus I in my numerator. So my z value is going to be 5 halves minus 1/2 I. So that number is going to be the solution of my equation. In lesson 1, we talked about complex numbers, how they are represented in the complex plane, their conjugates, and we tried to perform the 4 arithmetic operations on complex numbers. I hope this lesson was useful for you, and I will see you in the solutions to worksheet 1.